Okay. Thank everyone for social distancing and joining us in what is our second virtual Zoom thesis defense this semester. I hope everyone is doing well in this time. I have a brief welcome, some introductory remarks, and then I'll turn it over to Conor for a approximately 45-minute presentation. I'd ask everyone during the presentation to mute yourselves. Whether you shut off video or not is something else, but please mute. Following Conor's presentation, we'll have questions from the audience using the raise hand feature on the participants list in Zoom. We'll recognize you. And then following those question session from the audience, there'll be a closed session with the committee. And then I will send out an email sometime afterwards saying what happened.
With the virtual champagne, right? With the virtual champagne.
Yeah. On the left is Conor's cover from his thesis. You see the title and the names of the committee chairs. I believe Gunter's still a member of the IFA in some form or other, but we welcome Gunter from Europe, Bahram Mobashir from California, and Jason from just across the road in somewhere in physics, and the others from the IFA. My introductory remarks, Conor came to us from UC Santa Cruz. That's turned out to be a welcome relationship to the title of his thesis. He came very well prepared. He's been a graduate student at UH Manoa, master's and PhD, hopefully, degrees. And we like him so much, we hope he will accept a postdoc offer from the Dawn Center at the University of Copenhagen jointly with UC Riverside. I think he knows that, but we'll see. I thought I would just give you a few pictures to say what's happened during the course of this thesis. He didn't sit in a room. We traveled a lot, learned a lot, or I learned a lot from him. I haven't had a graduate student with his data skills in my entire career. I must say it's been a joy to work with him. This is Conor from Bateman's Bay. The koala is on the left and Conor is on the right. You see the koala has sort of flipped around. I don't know what's going on there, but these are the three Conors, I call it. Actually, the two of them are actually named Conor. I don't know what they gave the name to the koala, but I assume it's Conor as well. As I said, this is where chapter 2 of his thesis with the Sloan data was sort of conceptualized. Now, some of these pictures are a little out of whack, but only Conor knows that. So the rest of you can play along. This is Conor from Merimbula. A lot of his thesis work was done while he was in Australia. This was actually the genesis of chapter 3. He's talking to Lisa Cooley, a former faculty member, actually telling her what she missed in her PPT analysis a long time ago. That resulted in the work that was presented in chapter 3. Continuing on, after talking with Lisa, you can see we take a little time off. This is Conor from McLaren Vale. For those Australians, you know what Molly Duker is. And you can see Conor enjoying a wine tasting, which is quite memorable for me, actually. And this is Conor contemplating finishing chapters 2 and 3 of his thesis. Well, I didn't mean to go there, but it's out of order. This is Conor in chapters 5 and 6 from Copenhagen. Both the serious and the jovial part. Chapters 5 and 6. And then finally, Conor from Mo'ili. This is the Conor sign for time to write your thesis. I think this happened about a year ago. He can correct me if I'm wrong. With that, I turn it over to Conor for your 45-minute presentation, and I ask the audience, remind the audience to mute. Conor.
All right, thank you so much, Dave. Can you stop sharing your screen?
I'm going to try.
Okay.
What do I have to? Okay.
We're good. You're good. We got you.
Okay.
They're all set up. All right. Let me just get situated over here. All right. Thank you so much, Dave. That was a lovely introduction. That last picture was from the Bond dance, actually last summer. Japanese celebration of summer. Anyway, thank you everyone for being here on this lovely Zoom day. And I'm going to present my dissertation defense. So the title is The Role of AGN in Bulge Growth in Quenching the Galaxy Main Sequence. And here is my outline. I'm going to start with just some quick background and terminology so that we're at least all on the same page going forward. And then I'll start with our results from the local universe, and then move on to higher redshifts with galaxies in the cosmos field, a brief discussion of a couple add-on things that were not originally part of the dissertation, but we decided were relevant and useful. Then I'll give some conclusions and I'll summarize my future work. So getting started, background and terminology. Understanding the processes that regulate star formation in galaxies is essential to understanding the full life cycle of galaxy evolution. So one of the diagrams that we use to understand star formation in galaxies is this diagram here on the right, the SFR M-star diagram. So SFR is the star formation rate of a galaxy. It's measured in solar masses per year. And M-star is the galaxy's stellar mass in units of solar masses as well. So we're going to get really, really friendly with this diagram. I have over the last few years. So I hope I can share my love of it with you. This diagram is interesting because the star formation rate dictates, let me put it this way, is that galaxies don't just sit still in this diagram. The star formation rate is the rate of change of the stellar mass. So galaxies evolve and move through this diagram, and we can use that to study their properties and understand processes that affect them. So now moving forward, we have, I'm showing on the right, 300,000 galaxies from the Sloan Digital Sky Survey. So this is essentially the big view of everything in the local universe. So we have 4 orders of magnitude in stellar mass and 4 orders of magnitude in star formation rates. So this is pretty much the picture of really what's going on with galaxies, at least in the local universe. So the star formation rates here are coming from the MPA-JHU catalog, and they're determined from spectra. The stellar masses are also from the MPA-JHU catalog, and they're determined by fitting the optical to near infrared for photometry. To guide your eye a little bit here, I've put the Milky Way and an example elliptical galaxy on here, just to kind of orient you and situate you with where everything would be on this diagram. So in the early days, really before we had star formation rates, we were really just kind of classifying galaxies by their colors. And what we found was that there's a very strong bimodality in the distribution of galaxy colors. There's a large population of blue galaxies, and then another separate population of red galaxies, separated by this green region in the middle that's fairly sparsely populated. So the green region would be a transition between these two populations. As that kind of concept of blue versus red galaxies got developed, we realized that red galaxies form a very tight red sequence, and blue galaxies also form their own sequence above. And like I said, green valley galaxies in the middle are fairly sparsely populated. So there's not as many of them as the blue and red galaxies. So as we moved forward and got larger data sets of spectroscopy, and then in the future after that, infrared data, we were able to convert this color mass diagram to star formation rates truly. And that revealed that the star formation rates of blue galaxies are very tightly correlated with the stellar mass, their stellar mass. So this led to this concept of the main sequence of star-forming galaxies, borrowing from the main sequence for stars, and that it's a very tight relation that kind of describes the evolution and bulk properties of the population of galaxies like the main sequence does for stars. So in the future, in the rest of this talk, I'm probably going to mix saying main sequence and MS a little bit, but MS is always going to be main sequence. So quenching the main sequence, my big title is how is the role of bulge growth and AGN activity in quenching the main sequence. So quenching is the process of moving galaxies off this main sequence and down onto the red sequence. So here I'm showing two examples of potential quenching. This top one would be something that's happening fairly rapidly. And then this bottom one would be something that's happening a little bit more slowly. The top one we know really has to happen rapidly because we don't see any galaxies that have stellar masses greater than this. So really, once you hit this high mass, you really need to shut down quickly. It's kind of less clear how lower mass galaxies are quenching, and that's really part of what we're trying to address in this dissertation. Okay, so moving on to a little bit more of a cartoon kind of picture is that galaxies or disk galaxies, so blue galaxies are primarily disk shaped. They live on the main sequence and they grow in mass as they progress up the main sequence. They grow in mass and they grow in star formation as they progress up the main sequence. Disks grow bulges or turn into bulges as galaxies quench. So here I'm showing disks getting progressively larger, they quench, and we know that by the time they're quenched, they become these big round elliptical galaxies, so essentially bulge dominated. Black holes also grow in galaxies through accretion onto the nucleus. And when those nuclei or the black holes are accreting, they release energy, and we call them active galactic nuclei. So these active galactic nuclei are actually the brightest things, or at least some of the brightest things in the universe. So how do we quantify the morphology of galaxies? We can measure the bulge to total fraction, which is essentially how much light is in the central bulge versus how much light is in the central disk. How much light is in the central bulge versus how much light is in the total galaxy. So add up all the light from the galaxy and then just take the light from the bulge, divide the two, and that's your bulge to total fraction. Bulge growth, or black hole growth, sorry, is also inferred from AGN activity. So if you see an AGN, you know that the central black hole is actively growing. So galaxies on the main sequence generally have relatively small bulges. Like I said, they're disk-dominated systems, so they have bulge to total fractions less than about 0.3, whereas these quenched elliptical galaxies have bulge to total fractions more on the order of 0.7 or greater, so really dominated by the bulge. So the big questions for this dissertation are, how does the bulge to total fraction change as galaxies quench? We kind of know the different endpoints of the starting of main sequence galaxies that are disk dominated and these quenched galaxies that are bulge dominated, but we don't really understand very well how the transition between those two happens. And then a follow-up question is, are AGN present as galaxies quench? So moving forward, we're going to start with galaxies in the local universe. And starting with chapter 2 of the dissertation, the role of AGN in quenching. So we classify AGN using optical emission lines measured once again and provided in the MPA-JHU catalog. This diagram on the bottom is showing the BPT classification. This is the Cooley, the Lisa Cooley et al. 2006 classification scheme. And using so what each one of these diagrams is showing the ratio of two emission lines. So this is oxygen 3 versus H beta on the y-axis, then nitrogen 2 versus H alpha, silicon 2 versus H alpha, and O1 versus H alpha. So these are all strong emission lines, fairly easily detectable in most local galaxies. And using this, we can divide galaxies into 4 different spectral types according to their AGN activity. So star-forming galaxies are galaxies that live in this H2 region, so below this dashed line, and then also below the red line in the other 2 diagrams. Composite galaxies fall between here and also below the red lines in the other 2 diagrams. Composite galaxies are ionized. Sorry, I should say that what this diagram is really measuring is the dominant ionization source in these galaxies. So star-forming galaxies primarily dominated by star formation, pretty obvious. Composite galaxies are primarily thought to be a mixture of ionization from AGN activity as well as due to star formation. Then we have Seyfert galaxies. So the Seyfert galaxies are going to live above this line in the first diagram, and then on the top kind of half of the diagram in the other 2. Seyfert galaxies are these really strong luminous AGNs. So these are the black holes that are rapidly accreting, so really very bright and active galaxies. As the accretion rates decrease in for the AGN, you end up with something that's called a liner, or a low ionization nuclear emission region galaxy. And so, yeah, like I said, these are the kind of fading AGN, lower accretion rates, end up being more massive galaxies as well. So moving on to a paper that Dave was mentioning that we developed working with Lisa Cooley at these writing retreats in Australia. It was published in 2019 as McPartland et al. And here what I'm showing is the star formation rate stellar mass diagram for each of these 4 different spectral classes. So star forming galaxies on the left, composite galaxies, Seyfert galaxies, and liner galaxies. The thick black lines here are showing the median star formation rate versus stellar mass for the star forming galaxies. And the thin lines around it are showing the 1 sigma contours or variation. The red line below that is showing the median star formation rate for galaxies, for passive galaxies. So this was kind of the red sequence that we were talking about previously. And the contours enclose something like 25, 50, and 90% of each of the sample. So what we see here is that galaxies that have AGN in them form an alternate sequence that's essentially orthogonal to the normal main sequence. And sorry, I should also note that these white lines in each of the 3 diagrams are the median for the respective spectral class. So we can see that the distribution of AGN really picks up above 10 to the 10 solar masses and proceeds in a decreasing manner, essentially orthogonal to the main sequence seen in the left. So the big conclusion walk away from this was, yes, that AGN form a plausible quenching sequence. I should note here when I say that they form a plausible quenching sequence that we in no way have proven that the AGN are quenching, actually directly quenching, but we can definitely say that the AGN are associated with the quenching. So they're along for the ride. It's still unclear at this point if they're actually doing the quenching or not, but they're definitely present in these quenching galaxies. So breaking this down a little bit more and looking at distribution of spectral classes as a function of stellar mass, what I'm showing on the top panel here is just the fraction of each of these spectral classes in bins of stellar mass. So the white things are the passive galaxies. And here what you can really see is that once you get above really 10 to the 10.5, the fraction of star-forming galaxies is really dying out. So a lot of really early studies of the main sequence would often remove AGN because they didn't consider them to be like traditionally star-forming galaxies. But what we're showing here is that really those samples were biased because in the second panel, I'm showing now the cumulative fraction of the star formation, or sorry, this is just now just the cumulative numbers. So this is showing the fraction of galaxies above a given stellar mass. So what this is saying is that above 10 to the 10 solar masses, ambiguous, once again, sorry, I should explain what ambiguous galaxies are. Ambiguous galaxies are galaxies that fall in multiple different regions of that classification diagram. So their interpretation is a little bit unclear. And one of the things that we've actually come out of this dissertation is we need to understand these ambiguous galaxies more. But for the time being, we're mostly just going to focus on the star-forming composite Seyferts and Liners, where we have a better or clearer interpretation of what these galaxies are. So what the second diagram here is showing is that above 10 to the 10 solar masses, star-forming galaxies are less than half of the population. The bottom panel is now showing the cumulative fraction of star formation in galaxies greater than that stellar mass. So what you can see here is that above 10 to the 10.5 solar masses, star-forming galaxies are a subdominant component of the star formation rate in the actual universe. So if you're just looking at star-forming galaxies, you're really just missing a lot of the action of star formation in the local universe. Okay, so moving forward, on the right here, I'm showing the median star formation rate for these same SDSS galaxies. But I've now split it up into including different spectral types. So the blue line here is the same as the black line in the previous diagram. Let me just flash back to that. So that's the same as this black line here. And then the pink line is adding in composite galaxies. And then the orange line is adding composite and Seyfert galaxies. The green line is adding composite Seyferts and Liners. So what we see is that adding composite galaxies flattens the relation, the main sequence. This is maybe arguably more better called the SFR M star relation rather than the main sequence. The main sequence really would imply just the star forming galaxies, but including composite galaxies flattens the relation, and then adding Seyfert and Liner galaxies really makes the relation turn over, and really that's where quenching is evident. So I've also included a couple models from the literature, and I'm going to be using this Salim et al. Curved line in the future as a little bit of a reference for what quenching looks like in the local universe. So kind of takeaway points from this are that AGN make a quenching sequence of decreasing star formation rates and stellar mass through composite Seyfert and Liner spectral types. AGN are really the dominant component of the star formation in the local universe in high mass galaxies, and composite galaxies and Seyferts turn over the main sequence or the SFR-M star relation. Okay, so we've now addressed a little bit about the role of AGN. We next need to, the big other piece of this is what about bulges? How do bulges grow as galaxies quench? So this is showing just a really brief illustration of what we're talking about, at least in a profile sense, for the bulge and disk components of galaxies. So on the left here, I'm showing just the profile of a disk galaxy. So this is just showing the intensity or the log of the intensity as a function of radius. out to 40 kiloparsecs, for example. And so I should note that all of these galaxies, each one of these galaxies has the same total brightness. So this would be a pure disk galaxy, a pure bulge galaxy, and this would be a half and half disk plus bulge galaxy. And so you can measure these things by fitting models. Usually you would fit a two-dimensional model to images of the galaxy. And what I'm going to be using in the next couple of slides is measurements of this bulge to total fraction. So once again, taking the ratio of the light in the bulge versus the total light in the galaxy. I'll be taking measurements from the Smart et al. Catalog, which he measured with his code GIM2D. And for those in the know, the bulge component is a de Vaucouleurs profile, so a Sursic index of 4, and the disk component is an exponential profile with a Sursic index of 1. So once again, showing the same SFR M-star diagram for the 4 spectral classes, but now I'm coloring each of the bins by the median bulge to total fraction in each one of these bins. So really the big takeaway here is that once you get above 10 to the 10.5 solar masses, almost all galaxies have significant bulges greater than 30%. And then bulges grow systematically as galaxies decrease in star formation or as they quench through these AGN phases. So we find significant bulge growth in the majority of massive galaxies. Really the only thing I've added here that you didn't just see in the last slide is that really a very, very small fraction, only 4% of quenched galaxies have small bulges. So really by the time you've quenched, all the galaxies have really, most of them have really built up some sort of significant bulge. And as we showed, those bulges are growing progressively or systematically as the galaxies quench. So the next little subsection here is another project that Dave once again mentioned, I think in the introduction, that we started with Lisa Cooley. This is really only come together in the last 6 months or so, and it's kind of a bit of a work in progress, but we thought it was very interesting and really deserved to be included here. So sorry, this is a bit of a complicated diagram. What I'm showing here is once again those 3 classification diagrams that we showed. And the idea was when you're classifying galaxies into these star-forming composite Seyfert and liner classes, you're really throwing away information that you really have from the emission line ratios. So the idea was to study the properties of galaxies, kind of like we did in the last diagram where we're studying the median bulge to total fraction. We were trying to trace galaxies, how they move through these BPT diagrams. And what we were using for that is this D4000 index. I can get into the details of how it's measured later, but really the walkaway piece to hold on to is that it's an age indicator. It increases monotonically with the age of the stellar population of the galaxy. So that's shown in the background here with the contours. Redder is essentially older, blue is younger. So galaxies, star-forming galaxies on this diagram live on this what's called star-forming abundance sequence, which is really just a progression of increasing metallicity and increasing stellar mass. So star-forming galaxies kind of start up here and they move down there. And then what we realized was that there's actually 2 pathways through this diagram, one of which, this P1, goes up and really involves a transition through a composite, a strong Seyfert phase, and then ends up as a liner galaxy, which are essentially quenched, which like we saw in the previous diagrams. But there's also a second pathway where galaxies don't necessarily have to go through a strong Seyfert phase to reach a liner spectral class and become quenched galaxies. So once again, just a brief summary, galaxy, I didn't actually mention that, is that really this star forming abundance sequence is really a more fundamental analog to the galaxy main sequence. Galaxy main sequence, measuring star formation rate inherently takes some sort of assumptions and modeling. Whereas, the star forming abundance sequence is just direct measurements from the data. So it's an observable thing. So it's a very fundamental, it's a more fundamental description of really what's going on in galaxies on this main sequence. So there's two pathways through this diagram, one that involves a strong Seaford phase, one that does not. And both pathways involve an aging sequence. So galaxies get older as they go down the pathway. Okay, so that's really covering a big breadth of our knowledge of local galaxies. And now the really big next step was, we had all this data from the Sloan Digital Sky Survey, and there's so much power to having this really large spectral database and all these measurements, available. We feel like we understand, bulges grow as galaxies quench, AGN are along for the ride. So we understand that in the local universe, but now we need to really understand how these things change and evolve with time as we go back into earlier epochs of the universe's history. So moving to higher redshifts. For our analysis of galaxies in the higher redshift universe, we are using the Cosmic Evolution Survey Deep Field, here shown on the right. This beautiful image from Hypersa PrimeCam. So the Cosmos field is a 2 square degree field with roughly 100,000 galaxies at the redshift range 0.25 to 1.3. It has pretty much every single space-based and ground-based observatory has observed the Cosmos field. So there's deep data all the way from radio to X-ray observations. So it's really one of the best fields and data sets for studying galaxy evolution at higher redshifts. It's also got a large database of spectroscopic redshifts, which are important for luminosities and measuring masses and turning observed quantities into actual rest-frame quantities. And there's also, for the galaxies that don't have spectroscopic redshifts, they have very, very robust photometric redshifts determined from 30 plus bands of broadband and intermediate and narrowband photometry. So the quality of these photometric redshifts is almost like a low resolution spectrum. So I'm just going to show a quick zoom in of each one of these little dots in this previous image is actually a galaxy, and then zooming in on this, you can just see the beauty of this data. It's truly incredible. So one thing that became kind of clear in the last 10 years is that the main sequence is an increasing, its normalization increases with redshift. So really this is kind of the big picture that we had in 2015. This is a paper by Spiegel et al. And they compiled all the available analyses of the main sequence and showed that really there's a very consistent picture in the main sequence that most of the various studies maybe disagreed in subtle details, but when you kind of recalibrate everything onto a similar system, it really painted a very clear and consistent picture for the main sequence, where you have an increasing normalization with redshift and a relatively tight scatter as a function in star formation rate as a function of stellar mass. So then comes, I think the world of Dave then steps into the main sequence. So on the right, we have the main sequence a la Nick Lee from his 2015 paper. And so like we saw in the local universe, this main sequence features a flattening or turnover at high masses. And really the big improvement here was getting better star formation rate estimates from far infrared measurements from telescopes like Spitzer and Herschel. And so the far infrared is really an excellent tracer for star formation because I guess I kind of glossed this over earlier, is that optical and UV measurements of star formation, which had been the common way of doing this, are subject to dust extinction. So the dust blocks the UV light that is really coming directly off the stars. And so to measure the star formation from UV, you need to correct for that dust somehow. And that's always going to incur some sort of systematic uncertainties. The great thing is that dust that is absorbing the UV light gets heated up and re-radiates in the far infrared. And so we can use the far infrared emission essentially as a calorimeter to catch all that light and then re-radiate it in the infrared. So if you can measure the infrared, you can measure a very robust star formation rate. And from these very new robust star formation rates from Spitzer and Herschel, Nick Lee uncovered that the main sequence really flattens at higher redshifts. And that there's some subtle differences in the change in normalization for massive galaxies versus low mass galaxies. And so moving forward, I'm going to use this Nick Lee main sequence as kind of a reference to compare with our results. So moving on to AGN and quenching. Okay. So in the local universe, we had this BPT classification. However, this is really not possible right now in the cosmos field due to the there are many spectra that we can use to measure the redshifts of galaxies, but most of these spectra are either not deep enough or not high quality enough to measure these emission lines that we need for the BPT classification, or often the case is that we have, one or two of the lines where we need, what is it, 6 or 5? 4, 5. So we don't have the spectra right now to do the same BPT classification at higher redshift. So we need to use other continuum measurements to identify AGN at these redshifts. So we can use, I've laid out three techniques here that we're using to identify AGN at higher redshifts. Okay, where was it? Okay, so mid-infrared colors first. By using a color diagram of mid-infrared, so this is usually using Spitzer IRAC colors. You can also do this in the local universe with WISE colors. Essentially what you're doing is you're searching for signatures of emission from hot dust from an AGN torus. So the AGN torus is really a ring of dust around the accretion disk of the AGN that hot dust emits in the mid-infrared. So the cool dust that gets heated by star formation emits in the far infrared, whereas this hot dust that's heated by the more energetic processes of the AGN emits in the mid-infrared. And so when you have a strong AGN present, it fills in the mid-infrared region and creates a power law, and you can identify that as essentially red colors in the mid-infrared. So I'm using the Donnelly et al. Classification scheme for that. And then another way of identifying AGN is through X-ray emissions. So very luminous X-ray sources. Essentially, X-ray emission is produced by supernovae, but above a certain threshold, really, you can't make enough supernovae to make that much X-ray emission. So X-ray emission is directly tracing emission from the direct accretion disk of the AGN. And for that, we're using data from the Chandra Cosmos Legacy Survey from Chavano et al. 2016, using the optical counterpart identification of Marchesi et al. And really this work was pioneered by work by Hyewon Soo in 2019 and through her dissertation working with Günther. And so a third way that we can also identify AGN is through radio emission. So jets produced by the AGN emit synchrotron emission. which we can detect in the radio. Similar to the X-ray, the radio emission is also produced by star formation, or really produced by supernovae. So you need to identify things that have a significant excess of radio emission compared to what you would expect from their star formation rates. So we were using that measurements of that. So AGN identification from the catalog of Del Vecchio et al. This is coming from the Cosmos VLA 3 gigahertz survey. So starting with the mid-infrared AGN. So what I'm now showing is, once again, the star formation rate stellar mass diagram, but now divided into 6 bins of redshift. So going from 0.25 all the way up to 1.3 here. So this is covering about 8 gig years of the universe's history. So more than half of the universe's history. The purple points are showing these mid-infrared selected AGN. The downward pointing arrows are galaxies with upper limits in the star formation rate. The solid black line is showing the Nick-Lee main sequence for the respective redshift. And then the dashed line down here at the bottom of the curved line is the Salim-Edal main sequence, or sorry, SFR M star diagram that we talked about earlier for local galaxies. So this is the relation for all local galaxies. So what we see here is that, most of, excuse me, sorry, the mid-infrared AGN are distributed both above and below the main sequence, pretty much at all redshifts. They have a fairly broad range in mass. And one thing to note is that the upper limits in the star formation rate really generally fall below the main sequence for each one of the redshift bins, at least for these massive galaxies above 10 to the 10.5. So moving on from mid-infrared to X-ray sources, I'm now showing the same diagram except for X-ray sources. Here I've split the sample into 2 colors. The orange points are lower luminosity X-ray AGN, and the green points are higher luminosity X-ray AGN. We didn't really find any strong differences as a function of luminosity between the star formation rates of these galaxies. So I'm going to go, moving forward, I'm just going to combine these 2 samples. Similarly, we did this same thing with radio galaxies, or radio AGN. These overall have their star formation rates are a little bit lower. We see fewer of them above the main sequence. More of them have upper limits in their star formation rates. Okay, so this has been an interesting little look at the distribution of these galaxies. So, like in the local universe, AGN are found in primarily massive galaxies. But it's kind of hard to directly see what the star formation rates, or the average star formation rates, or the mean star formation rates are of these galaxies as a function of redshift. So I've went ahead and done that for you. Yes, so I've included the upper limits here, at least as the best we can. And what we really see is that the mean star formation rate for each of these AGN classes, so sorry, I should note that I've now combined once again the 2 samples of radio AGN split by luminosity. There's a consistent progression towards decreasing star formation rates between the mid-infrared, X-ray, and radio AGN galaxies. With really the mid-infrared things, like I said, being the highest star formation rates, the X-rays falling in the middle, and the radio AGN falling at the bottom. One thing to note about this diagram, sorry, I didn't explain the units here. This is the offset from the main sequence. So really this is measuring the distance in star formation rate. So the distance below or above the main sequence in terms of star formation rate. So the log of the star formation rate divided by the star formation rate. I should actually say not just for that redshift, but also for that mass. So this is offset from the main sequence is what we're showing in the y-axis here. And so the top of this chart here is showing an offset of 0. So main sequence galaxies would live all along the very top of this. So each one of these AGN classes are below the main sequence, at least in the mean, and progressively decrease through mid-infrared, X-ray, and radio AGN. So this is really interesting and exciting because it's kind of very similar to the sequence of decreasing star formation rates in AGN that we found in the local universe. How does this compare to those local galaxies? And I've shown that here. So the purple, green, and red stars are now showing the composite Seyfert-2 and liners in the same diagram. So this really adds confidence that the mid-infrared AGN are similar to the local composite galaxies. The X-ray AGN are similar to local Seyfert galaxies, and the radio AGN are similar to local liner galaxies. However, I'm going to talk about this a little bit more in the future work. We really need to do more work to unite all of these AGN classification techniques. Really, we need spectra for the galaxies at higher redshifts where we have these good X-ray and radio mid-infrared data, and we need deeper mid-infrared X-ray and radio for the local galaxies that have the already measured spectra. So just quick summary from this. Yes, I should also note this paper will be submitted hopefully later this year. And really the big walkaway is that there's the systematic decrease in star formation through these mid-infrared X-ray and radio classes. And we find very strong similarities between the properties of these AGN at high redshift with the AGN that we see in the local universe. Okay, so moving on to bulges in the higher redshift universe. So using that beautiful hyperspace prime cam data that I showed earlier in the introduction to Cosmos field, we fit roughly 100,000 galaxies with the code galfit-m, which does a simultaneous fit allows for a simultaneous fit to multiple bands. So we were fitting the HSE GRIZY band simultaneously using a bulge plus disk plus nucleus model. So once again, the bulge is a de Vaucouleurs profile. The disk is an exponential profile, and for the nucleus, we're just treating it as a point source. The nucleus was really just an exploratory thing to add to it. So what I'm showing here is really the decomposition results for a big disk galaxy. So this is showing, this is the original image on the left panel in each of the GRIZY bands. This is the combined model, bulge plus disk plus nucleus model for each of these bands. And then the following columns are showing just the disk component, just the bulge component, and just the nucleus component. So this galaxy really does not have a strong nucleus component whatsoever. And then finally, this rightmost panel is showing the residuals. So you can see the spiral structure in this galaxy pretty clearly in the residuals. And then just showing one more example of a strongly bulge-dominated galaxy here. So this is, B over T. So this is really something, that lives down in that quench regime, with a large bulge-dominated galaxy. And for here, you get pretty good residuals because the galaxy is fairly smooth. So like I said, we did this for 100,000 galaxies throughout the Cosmos field to really try to extend what we learned about bulges in the local universe to higher redshifts. And this is what we find. So this is once again showing roughly the same 6 redshift bins, going from 0.25 now to 1.2. The black solid line is once again showing the Nick-Leodol main sequence. The dashed line is showing the Salimidol local SFRM star relation. And what we're seeing here also is that at high masses, we see an increase towards, about 30% or higher bulge fractions in really all massive galaxies, and a systematic increase in the bulge to total fraction as galaxies move down in star formation rate and quench. This is really exciting and interesting. One thing that's a little bit different about what we did, because we don't have quite the numbers in the Cosmos field to do a full separation by AGN class. This is not so directly comparable to what we did in the local universe in chapter 2 or the earlier sections of my talk. So I've now taken those things, taken all of the spectral classes and combined them for the Sloan Digital Sky Survey galaxies, and here showing them on the left. And so really, this just really echoes that the trends that we're seeing in these high redshift galaxies, or higher redshift galaxies, I should maybe say, are very similar to what we see in the local universe. So really, the relationship between bulges and quenching has really stayed the same for the most part over the last 8 gigayears. This paper is also going to be submitted later this year as McPartland et al. 2020C. And so our big kind of walkaways for this are, we measured bulge to total for around 100,000 galaxies in the Cosmos field, and trends in bulge to total are very similar to what we see in the local universe. Okay, so now we're going to jump into a discussion. Really, this dissertation could have ended right here with these major findings. Bulges are really involved in this quenching process. They're growing systematically as the galaxies decrease in star formation and quench. And AGN formed this sequence that really peaks in the Green Valley, in this transition region between blue and red, or star forming and passive galaxies, star forming and non-star forming galaxies. And for most part, is what we can see is that all of these trends, at least for AGN and for bulges, persist over the last half of the age of the universe. A couple important questions that this has not addressed is how does the fuel for star formation get consumed during quenching, and really what is triggering the quenching? So we just briefly explore 2 kind of ideas for this. Is, do galaxy mergers potentially trigger quenching and trigger AGN? And how much fuel is available for star formation in the form of cold gas, of molecular star forming hydrogen H2 gas and atomic H1 gas? So starting with galaxy mergers. Really, the galaxy merger paradigm. So what I'm showing here is this is kind of an evolutionary sequence proposed by Hopkins et al. This is from their 2008 paper, but they have a whole series of papers on this. This is really, in many ways, Dave kind of led into a lot of the background for this work. But the idea is you take, your disk galaxy, and through a merger, you can both produce an AGN and convert the morphology of the galaxy from a disk-dominated morphology to an elliptical morphology. So mergers can grow bulges. This is work that Josh has shown in his earlier days. Mergers can also convert atomic hydrogen H1 into H2. So you can take fuel, or really gas that wasn't directly forming stars, and make it into a form H2 that will go on to directly form stars. And then mergers can also fuel AGN. So really, this is all because the mergers produce torques that drive gas into the center of the galaxy. That gas gets condensed and then converts into H2 that can fuel a nuclear starburst and also fuel accretion onto the AGN. So one of the original thoughts for this dissertation was to directly measure this. It's fairly hard, actually, with the current data we have. So we ended up with a more indirect approach, I guess I should say, of comparing the fraction, you know, the number of mergers to the number of AGN, at least to just see if this is a viable, you know, production mechanism. Can mergers explain the population of AGN? So what I'm showing here on the right is the same 6 Redshift bins that I've been using for the last few slides. The black lines, the black curved lines are showing predictions for the merger rates from the Illustris simulation, which is a new cosmological hydrodynamic simulation. It reproduces lots of properties of the real universe and is really kind of the state of the art for cosmological simulations these days. Big boost, the big improvement that Illustris brought to the world of cosmological simulations, and specifically for measuring the merger rates of galaxies, was that earlier simulations that really only simulated dark matter had to kind of artificially paste galaxies into these dark matter halos. And so there's a lot of assumptions that go into that. Illustris is able to directly simulate the galaxies, so you can just really directly calculate the merger rate coming out of the simulation. So once again, the black lines are showing the merger rate as merger rate per galaxy per gigayear. So equivalently, you can really just consider that to be the fraction of galaxies at a given mass that are undergoing a merger in the last gigayear or so. The top line, the solid line is showing major mergers, so mass ratio of 1 to 4 or greater. The dashed line is showing major and minor mergers, so up to a mass ratio of 1 to 10. And then the red line is now showing the fraction of AGN as a function of mass using the sample, the Cosmos sample of X-ray, mid-infrared, and radio AGN. So I've just combined all 3 of those groups and calculated the fraction as a function of mass compared to all other galaxies. And really what we see here is that there are enough mergers, at least major, you know, in these higher redshift bins, enough major mergers to really explain the entirety of the AGN population. And in the lower redshift bins, we need a small contribution for minor mergers, but the numbers at least match up. So there are enough galaxy mergers to explain the population of AGN in the cosmos field. Okay, so moving on to the cold gas content of galaxies, we really, like I said, this is kind of outside of the scope of my original plan of my dissertation, but this started from a project of when this Alfalfa survey was released, I got very excited, and I think Dave did too. Alfalfa is a blind flux limited survey with Arecibo, so they pretty much just surveyed a strip of the sky that was you know, easily observable from Arecibo. And this is really nice just because there's no pre-selection, there's no selection effects that go into, well, there's flux limit effects, but there's not pre-selection effects of, you know, the galaxy sample that they decided to observe. So Alfalfa lines up, you know, I think Alfalfa covers roughly half of the SDSS region. So I should note this is really only for local galaxies. The currently highest redshift H1 detection is something at Z of 0.35, and that was pretty monumental effort. So all these galaxies are at very local redshift, so less than 0.06. The X-gas survey was a follow-on survey to the Arecibo survey. So pretty much they were trying to get a more unbiased look at galaxies with less H1. So really they just selected things by stellar mass and a specific redshift range. And so I'm showing all of these galaxies on the right. The grayscale bins are showing the log number of Alfalfa galaxies in each one of those bins, and the little diamonds are showing the X-gas galaxies. This whole mess down here is just showing upper limits from the X-gas survey. And X-gas, they were just doing a mass fraction limited survey. So that's why this has got a slope of 1 here. So, you know, they're, I think, going down to something like 1%. And if they, you know, otherwise they just say it's got to be lower than that. The red line here is showing the median H1 mass as a function of, so yeah, sorry, I should say this is showing H1 here on the left. It's no longer star formation rate. So the red line is showing the median, and the little thin lines above and below are showing the 1 sigma variation. Really the walk away here is that there's really large H1 reservoirs in many galaxies. So above 10 to the 10, right? The median is something like 10 to the 10 or greater. So most galaxies, at least normal, you know, active star forming galaxies, have large reservoirs of H1 gas that could really go on to fuel star formation for at least a few gigayears, if they, you know, can find a way to convert that H1 into H2 gas that actually goes on to form stars. So speaking of H2 gas, we also collected H2 measurements, or really CO measurements from the literature that give us measurements of the cold molecular gas that's really going on. So this is really the fuel for star formation. So first, the biggest sample that we're using is the X cold gas survey. So this is really just an extension of this X gas survey that we were using previously for the H1 masses, using the ERAM 30-meter telescope. And then we also pulled in the GOLS galaxies, which are local luminous infrared galaxies, and FCRAO, which is pretty much mostly blue disk galaxies in the local universe. Now I'm showing here on the y-axis is the H2 mass versus stellar mass. I've copied over that same median line from the Alfalfa galaxies here just for reference, so you can compare. And what you can see is that the slope of the H2 to stellar mass relation is much steeper than it is for the H1 to stellar mass relation. So, you know, really you don't find large reservoirs of H2 gas until you get into galaxies that are, you know, above 10 to the 10 or so solar masses. And really you know, so you can get reservoirs, or sorry, cold gas contents or molecular gas contents that are on the order of the H1 gas content, but really that only is occurring in massive galaxies. This actually also kind of mimics the main sequence in some way, in that you have this tight slope at the bottom that then kind of turns over and maybe flattens a bit in higher masses. So it's just summarizing these final results of the gas content. Predicted number of major mergers is sufficient to explain the population of AGN. We have a lot of H1 gas that is really available for star formation if we can convert it into H2. And H2 masses are strongly dependent on stellar mass. And finally, when galaxies quench, it's associated really with a big decrease by at least an order of magnitude in the total gas content. Okay, so we're almost there. And now we have conclusions. So big walkaways from this dissertation: local AGN, form a quenching sequence. Once again, I should highlight that, you know, this dissertation has not proven that AGN are causing the quenching, but has shown fairly convincingly that AGN are associated, very closely associated with the quenching process. They're found in galaxies that are actively quenching. Similarly, bulges have already grown, you know, galaxies have already grown a significant bulge by the time they get to stellar masses greater than 10 to the 10.5 solar masses, and those bulges continue to grow as galaxies quench. Analysis of the ages of galaxies in these BPT classification diagrams revealed that there's Sorry, I just realized this should not have Seifert. This is my bad. So analysis of the properties of galaxies in these BP2 diagrams revealed that there's a second pathway. So the first pathway was composite Seifert to liner. Second pathway does not include the Seifert galaxies. So just going through composite and liner phases. And both of these pathways involve an aging sequence. So the galaxies get progressively older as they go through these different phases. Results for the higher redshift, there's a similar decrease in star formation through mid-infrared, X-ray, and radio AGN. So this higher redshift continuum selected AGN provide really plausible analogs for the AGN that we see in the local universe identified through their optical emission lines. We find really similar trends in the bulge total fractions for galaxies out to Z of 1.2 as we see in the local universe. Once again, just bigger bulges and massive galaxies and a systematic growth of bulges as galaxies quench. Major mergers do provide a reasonable explanation for the production of AGN, and massive galaxies have large H1s reservoirs, and you really only get significant H2 reservoirs once you get up into the most massive galaxies, and quenching is associated with a decrease in the total gas content by at least an order of magnitude. So that was a lot. This work has really inspired a lot of future analysis and really important questions of follow-up. I'm just going to briefly summarize here. One of the things that I mentioned in the introduction to the higher redshift AGN studies was the need for larger samples of spectra of really just unbiased, complete samples of just the general galaxy population at higher redshift. It's also good to just start with just the AGN population so that we can reconcile these different AGN classification techniques from radio, X-ray, mid-infrared with optical emission line classification that we're using in the local universe. So there's a few instruments that are really going to revolutionize this field in the near future. Really, the first is VLT moons that just got put onto VLT this year. On the left, I'm showing a comparison of existing and these future next generation spectrographs. So people at the IFA probably know Deimos and LRIS very well. VMOS here is shown with these four green boxes, and this new VLT moons instrument is shown here with this red box. So it's definitely a huge improvement over existing instrumentation. It's going to be able to do something like 1,000 spectra in one shot. So that's really going to speed things up. I mean, I think I've done my Deimos runs, and I think 100 sources is probably optimistic for a Deimos mask. So being able to, a factor of 10 increase in the ability to gather spectra is going to be a really, really big game changer. Other future instruments that are coming in the near future or coming online soon is PFS for Subaru, the prime focus spectrograph. That is shown as the field of view here in the purple circle. So essentially you can observe the entire cosmos field at the same time. This really is going to help a lot with if you wanted to observe all the Xray AGN and cosmos, you probably have to do multiple masks. But, partly because of the number of sources, but also just because the field of view is insufficient. If you're looking with something like Deimos, you'd have to do many repeat observations to get the entire field covered. So PFS is going to be able to do 2,000 spectra, and it's going to be available in late 2022. And then in the further future is the Mauna Kea Spectroscopic Explorer. Their specs say that they're going to have at least more than 3,000 fibers, or so ability to gather more than 3,000 spectra simultaneously in an even larger field of view. On the right here, I show the redshift coverage for each of these emission lines that we would be using for the BPT classification that we used in the local universe. So PFS is really going to be able to push us out to something like Z of 0.9, and then with something like moons or MSE, we can push out to even further redshift. So this is really going to change how we are able to study the population of AGN at higher redshifts. So one little last final slide of future work. So AGN identification using PFS really is going to be a big goal for my future career. Other all-sky surveys like the VLA all-sky survey, VLAS, and the eRosita all-sky survey are going to provide deeper X-ray and radio observations for local galaxies. So that'll kind of help to bring all these pieces together of having deep, large, robust samples of AGN identified through X-ray and radio in the local universe, and larger samples of AGN identified through optical emission lines in the higher redshift universe. Improving on the galaxy morphology stuff that we did with the Bulge to Total. The Euclid Space Telescope is really going to blow a lot of things out of the water for that. The all-sky survey from Euclid is going to really it will allow us to measure, merger fractions and bulge to total ratios in local galaxies on a completely different level than the current SDSS data is allowing us to do. And we can even do much better bulge to total or bulge to disk decompositions for galaxies in the cosmos field, really out to Z of 1.3 and less. Finally, one of the things that we brought up or got brought up through this gas analysis was the need for deeper gas data. So the FAST telescope in China, 500, it's 500 meter aperture telescope. So this is kind of Arecibo 2.0. It's got a survey speed that's 10 times better than Arecibo. So it's going to just completely clean up and have amazing surveys of the H1 content in galaxies that can actually detect a galaxy with 10 to the 10 solar masses of H1 at Z of 0.7 in an hour. So this is completely going to be a game changer. And then the LMT telescope in Mexico is 50-meter dish. It's gonna really change the game for observations of molecular hydrogen gas content throughout the universe. And the cosmos field has already been marked as a early science field. So there's going to be lots of exciting new observations coming in the cosmos field. And with all that, I would like to say thank you. Brief just acknowledgements. Thank you to my advisor, Dave Sanders, and thank you to my committee. Thank you to Lisa Cooley and the Astro 3D collaboration for all of these writing retreats, and really they've inspired many of the papers and the work that I've done throughout my dissertation. Thank you to Andrew Repp for putting up with me, asking him questions all the time in the office. And also thank you to the rest of my cohorts, Sam Grunblatt at Math Service. I hope they're all doing well. Thank you to the Cosmos team. Really stimulating scientific discussions and really fun team meetings. Thank you to our local H2O team. It's kind of really the thing that's secured my future as a postdoc. And a big thanks to my my REU students, Martine Loken and Justin Johnson, and then the other REU students I've worked with, Kurt Hamblin, Jason Brewster, Chris Bain, and Caitlin Lilly. Big thanks to Heather Flewelling and Conrad Holmberg for all of their help with Pan-STARRS data access in the early days of my dissertation. And then really thanks to all of the great secretaries I've worked with, Susan Lem, Lori Unruh, and Amy, just saving my life for all the travel I've done. And really big thanks, especially for today with all of this Zoom defense meeting, to all of the IT staff, Kurt Dodds, Gavin, George and Raja. Really made all of our lives much easier, especially today and in this current pandemic fun. And big thanks to Bill for, what was the line? Hottest finger gun in the West. Big thanks to my family and friends. And with that, I'll take any questions. Put up my conclusions.
Thank you very much.
Well, thank you, Conor. I only see the thesis committee on my participants list. So if people want to ask questions, maybe someone else can see the full list of participants. If you want to raise your hand.
There's a bottom which is called participants on the lower left, which you click, and then you can see.
I had clicked on the wrong one. You're right.
Like Harold has a question. Harold, I think you
Hey, hi, Conor. So before all, outstanding work. Thank you very much. I particularly appreciated your introduction, which I think was the best I've ever heard about the field in general. But I want to challenge your big picture a little, and at the same time throw you a softball. So you painted this picture of galaxy evolution being driven by mergers, all the way from spirals to red and dead ellipticals, and then you showed how the merger rate is completely consistent with
No, I have to do it later.
Fractions, and all of that works beautifully, except for that final step, because ellipticals, of course, as we know, all live in a very special environment, which is a high density environment. And in that environment, mergers actually do not work as a driving mechanism of galaxy evolution. So since you wear another hat too, at least you did in your early days, so when you were a cluster person, perhaps you can educate us about what could conceivably get us through that final step of galaxy evolution. How do you create those ellipticals? It's not mergers.
Yeah. How do you go from the last mile question?
Right.
Galaxy mergers can build up a bulge, but getting it into a final state of an elliptical. Yeah, so I mean, there's all sorts of galaxy interactions. So essentially, tidal force. Who's the loud mic? Is that you, Harold, or no? So essentially, gravitational torques from interactions in a high density environment. So a cluster will kind of over time pull randomize the orbits of stars in the galaxy and make it into more of an elliptical. As you maybe noticed, the quenched galaxies that we have in, let me see if I can go back to that. I didn't really comment on this, but here, that this really only goes up to 70%. So these quenched galaxies, when I say they're becoming ellipticals through this quenching thing, it's maybe a slight overstatement. It's really just that they're becoming bulge-dominated galaxies, and yeah, you probably need some sort of environmental interactions to stir things up to get them to become fully elliptical galaxies. Okay.
Okay, other questions?
Eastman got a question. Oh.
Istvan?
Talking permitted. Istvan. Yeah, you're good, Istvan. I can't hear you though.
He is unmuted, so Istvan, speak.
Okay.
He has no audio.
Okay.
Can't hear you, Istvan.
He's speaking.
Well,
maybe he can ask his question through the.
Yeah, if you want to type it in.
Could we move on to the next person?
Chat?
Yeah.
Okay.
Oh, now we can hear you, Istvan.
Yes, Istvan.
Okay. This is weird. The whole Zoom came up completely differently than normally. I don't know what happened, but.
It's slightly different than normal Zoom. Anyway.
Okay. So no, my question was, so you established all these interesting trends about quenching and formation. If you try to translate it into physics, like what kind of physics do you think this implies? In terms, in just simple terms, like for the black holes and the interaction of the gas, gravity, and so forth. So is there any statement that you might be able to make at this point, or it needs further research? to turn
Yeah, I
this?
mean, like I said, I can't really make any direct claims about what's actually driving the quenching. I mean, AGN have been long kind of posited as, or I guess I should say AGN feedback has long been kind of suggested as a mechanism to quench star formation. Really, they need it in cosmological simulations to reduce the massive galaxy population. So if you don't have something like AGN feedback acting in massive galaxies, you actually end up with galaxies that are too big. And so when I say AGN feedback, that really means for, you know, these luminous Seyfert galaxies, that looks like something like radiative feedback. So the AGN accretion disk is so bright that it drives essentially winds out of the galaxy, and that can cause this blowout that we showed in the, here will be this kind of blowout phase before you end up with kind of a traditional, quasar. Lower luminosity, or sorry, lower accretion rate AGN primarily produce feedback in the form of jets, which actually heats the gas and kind of prevents future gas from continuing to cool and form stars. But yeah, like I said, we can really only say that the bulges, you know, bulges are growing through the quenching process, and that AGN are you know, popping up as galaxies quench. We can't really say from this work if, you know, if the bulges are actually quenching the galaxy or if the AGN are quenching them directly.
And what further observations could beside this question?
Yeah. So I've kind of been thinking about that a lot. So, you know, one thing that you could do, or that would kind of clarify this, would be, you know, searching. I was going to put this actually in my future work, but got chopped out. But would be searching for, you know, signatures of these outflows. You know, there's all sorts of IFU data sets now where you can look at ionized gas as a function of position in the galaxies. So searching for outflows in the form of ionized gas through IFU data, or searching for colder gas outflows through something like, you know, ALMA data. I haven't really, I've seen a couple papers about it, but it sounded like it was not super conclusive yet.
Okay. Should we move on to the next question?
Sure.
Two more, I believe.
Who is Flame Princess?
I see FP.
That would be me. Oh, Connor, can you hear me?
Yeah.
All right, sweet. So the talk was excellent. Thank you for sharing this with us. It looks like you've done a significant amount of work in a pretty short amount of time. So that's cool. I had just some specific questions about some of the earlier slides. So you had a type versus M star slide where you introduced sort of a large fraction of the population that you called ambiguous. I kind of just wanted to know, what is ambiguous about them and why aren't they easily characterized?
Let me, yeah, I was kind of trying to brush that under the rug a little bit. So ambiguous galaxies, no, it's actually, this is one of the things, honestly, one of the things I really want to look into in more detail in as kind of follow-up work, something that you can really do better with this IFU data, integral field unit data, is, you know, if you have spatially resolved spectroscopy, really, because, you know, all of these galaxies we're looking at right now is we just have one spectrum for the whole galaxy. So you don't know, like, if you have something going on in the center versus something going on in the outsides. But to answer your question more directly, an ambiguous galaxy is something that, say, it would be classified in this, you know, leftmost diagram as a star-forming galaxy, but it then ends up as a liner here in the. Can you see my pointer?
Yes.
I can.
Okay. So yeah, pretty much, it's got two different classifications in these diagrams. So to be considered a star-forming galaxy, it's got to fall in the star-forming region of each diagram to be considered.
Okay, so that's actually really interesting. I could ask you more about that a little bit later.
So some of it is assuredly driven by the signal to noise of the emission lines. For that analysis, I was not being, for example, in the pathways to quenching analysis, I was really strict about what I was including there, like only the things with like the really best measurements. But if you do that, if you restrict, loosen that restriction a little bit, you end up with a lot of galaxies that have lower signal to noise lines. So the O1 line specifically is fairly weak. So you can have that be, you can have that kind of scatter around a little bit. That's partly why this is so broad down here.
Okay.
Like I said, this is definitely an area for follow-up that I'm really interested in looking at.
The next question was Ben, I believe.
Hi, Connor. Great work. I had a quick question and point of clarification. You had a comment where you said the X-ray, near IR, and radio corresponded, and the higher redshift corresponded to Liner and Seaford in the local universe. If you go back to that slide, I forget what number it was, probably like 30-ish. Is that just the rank ordering, or is there something deeper I should be getting the connection between like those two populations when you plotted the start? That's exactly perfect.
Yeah, so I think yes and yes a little bit. Really, the statement I guess that we're trying to make is, yeah, the rank ordering is that they follow similar patterns in the offsets in the star formation rates. However, radio AGN, lower luminosity radio AGN often have liner-like emission lines, and the Xray AGN often have Seaford-like emission lines. So there is a lot of matchup. The MidInfrared AGN often have composite emission lines as well. But this is kind of part of what we really, like I said, what we need to do more of is really understanding how these things overlap and how, a mid-infrared selection might bias you, or, identify really a different population of AGN than composites. So really we need a data set where we have all these data together so that we can kind of understand, each one of these things is identifying a different piece of the AGN life cycle. So being able to combine them all together, understand what the biases of each one of the selections is giving you is really important work to do. And so Conor Augie is actually going to be doing part of this as his dissertation, because he's going to be getting kind of a complete sample of BPT lines for at least X-ray selected AGN.
Awesome. Thank you again, and great job.
Great.
These are all very good questions.
Yeah, no, great.
I was even expecting to have. If there are no more questions, maybe we should thank Conor again and then proceed to our closed session with the committee and Conor. So thank Conor again.
Yay!
Well done, Conor.
Oh boy.